best understand the motion of the helicopter, we can graph the x and y components of its acceleration, velocity, and displacement functions. Looking at the x and the y component of its acceleration functions, you can see that in the x direction, it begins with a large magnitude of acceleration, of positive acceleration, that steadily decreases until time equals 0 before its acceleration then goes negative all the way until time equals 10. This suggests that in the x direction, the helicopter accelerates greatly in the beginning and its acceleration decreases until halfway through its flight, where its acceleration then goes negative. The speed of the helicopter starts decreasing until its flight is finished. In the y direction, the helicopter starts with positive acceleration, suggesting that maybe it lifted off the y direction before its acceleration then becomes negative and then approaches a y value of 0 as time gets closer to 0. This suggests that in the y direction, it accelerated upwards and then maybe slowed down to achieve level flight until time equals 0, where then we can see a small positive acceleration before a lot of negative acceleration, which shows it coming to a landing. Next, we can look at the x, the y components, the helicopter's velocity function, the x given in red, the y given in blue. From -10, the x direction, you can see velocity increasing very quickly from -10 to 0, where its velocity after 0 then starts to decrease and approach 0 on the y-axis as it approaches time equals 10 for the x-axis. This suggests in the x direction that the helicopter's velocity is increasing until halfway through its journey, where its velocity then begins to decrease until it comes in for landing. Looking at the y component of the velocity, we see a small positive velocity beginning before its velocity goes back to 0 until more than halfway through the flight. You see another positive velocity and going back to 0. This shows that maybe the helicopter went off the ground, had positive velocity in the y direction before it then around 5, maybe 4, velocity went to 0, which showed that the helicopter was in stable level flight, wasn't accelerating, didn't have any velocity in the y direction until it came in for landing at time equals 10. Next, we can look at the x and the y components of the displacement function. Looking at the x component, if we zoom out here, we can see at time equals 10, it had a large negative displacement, and by the end of the flight, had a large positive x displacement. This just suggests that it covered a large amount of distance or on the x-axis during its flight. Zooming in to look at the y component of its displacement, you can see that it starts off negative but ends positive, with a large flat part in the middle. To best explain this, it would suggest that maybe the helicopter started its flight in a valley or somewhere where the land was somewhere below maybe sea level or whatever we want to set the origin as. It then took off from this valley, let's say. It had level flight from maybe -2 to +2 in time before coming in for a landing, maybe on a hillside or a cliff, which is what this large positive y displacement shows.
Today I'm going to be sense making this helicopter problem. First the graphs, then the equations. So for the acceleration graph, in the x direction, this does make sense for real life. And the big idea here is that the equation for acceleration is the change in velocity over the change in time. And we see that this graph on the bottom for the red, I guess the derivative of this is the acceleration. So this makes perfect sense for why our acceleration graph looks like this. We can also see this for the y direction. Makes sense in real life. And we know it's the change in velocity over a change in time. So it's a derivative of this bottom graph, and it makes perfect sense, right? We can also see this for velocity graphs. We see the derivative of this green, graph is going to equal the red graph, right? And this makes sense, right? The change in position over the change in time, right? The slope for green is always positive, just like red is always positive. We also see this for the velocity function in the y direction. We know that it equals change in position over change in time, which is exactly what we see here. And then for position, it just makes sense, right? In real life, it makes sense that we're always moving in the x direction. And for the y direction, it makes sense that we're always going positive and we don't go below where we started, right? Maybe we could if there's a valley or something, but in most cases, if it's flat ground or near flat ground, you're not going to go, super far into the earth. All right, now I want to sense make for each equation. We assume that t is positive because time must be positive. We also assume that a is positive because the acceleration must be positive at the beginning, right? If a was negative, then we'd be accelerating downwards when we're already at the ground, and that just doesn't make sense, right? So now we can look at our acceleration equation. As we increase b, acceleration increases. As we decrease b, acceleration decreases. Now we're dividing by capital T. So as we increase capital T, we're actually going to get a smaller acceleration. And as we decrease it, we're going to get a bigger acceleration. This is true for the y direction as well. As we increase a, bigger acceleration. As we increase t though, capital T, we're going to be dividing by a bigger number, so we're going to get smaller acceleration. Now, this is also true for velocity. As we increase b, we're going to get a bigger velocity. As we decrease, smaller velocity. And then we're also dividing by 2t in this x direction, right? So as we increase t, we're going to get a smaller velocity. And as we decrease t, we're going to get a bigger velocity. This is also true for the y direction, right? For the same exact reasons. We can also look at the position. It's true for the position as well, for the same exact reasons. Increase b, the position is going to get, greater. We decrease b, the change in position is going to be less, right? As we increase capital T, we're going to be dividing by a bigger number, so we're going to have a smaller change in position, and the inverse is also true. And then for the y direction, for position equation, we're going to, as we increase a, we're going to get a bigger change in position. As we decrease a smaller change in position, and the same is true or the opposite is true for t. As you increase t, we get a smaller change in position. Decrease t, we get a bigger change in position.
The best way to reflect back on the helicopter problem that we explained and discussed is to have kind of similar and simpler ones we took before, either in class or studio. For the first example I'll be discussing today is the one we used in the practice quiz 1B solution to make a comparison between the helicopter and the runner's problem. As we can see, they both use integration here to get the position as a function of time, but for different uses. In the runner's problem, it is used to decide the distance between the two runners within a specific time, whereas the helicopter problem is made upon changing variables and assumptions. Also, we can see that in the helicopter problem, we use the x-axis and y-axis, which means we need to work on both the vertical and horizontal part. On the other hand, the runner's problem only uses the x-axis because we need the distance only. Moving on for the second example, I'm using the second problem and the solution video of homework 2, where the requirement is to get the distance between the two lights. The similarity here is that we use Desmos for both problems to get a more accurate idea of what is happening in the function of velocity of each problem, where we conclude that v, which is the maximum velocity of the car in the homework problem, and beta in the helicopter problem is controlling how big the graphs get. Also, we can see from that, from what we can understand, that the displacement gets bigger and bigger the more v and beta increases in both graphs. Thank you.